homework assignment. At the end of class, we didn't have a chance to do any of these, and some of them were a little bit tricky. So did we have issues with problems like 12 or 14? Were you guys able to do those? Were they difficult? Were you okay with them? We were good? 12 and 14? If you look at your assignment, you got those done? 12 and 14 we were okay with? Yes? We got it? We're good? Yes? Okay. So if you want to check your answers for those two, 12 should have been 9 and 14 should have been 10. X equals 9, x equals 10. Did we get those? Yes. So you were not finishing the packet last night, you were just doing 1 through 16. That was the goal. Okay. Everybody was good? You're all good? Okay. All right, so let's look at the rest of the notes. We are on circle conjecture 8. Looks like this. Okay, so if an angle is formed by 2 secants or 2 tangents, so the picture can look like that, or if it's 2 tangents, I'm going to draw a little picture so you guys can see it. If it's 2 tangents, it would look like this. So it can look either way. If they intersect outside a circle to form an angle, here's the angle, then the measure of the angle is the measure of the big arc minus the measure of the little arc, and I'll label those in a second, divided by 2 equals the measure of the angle. So I'm going to go ahead and label these. Here is the big arc. Here is the little arc. So big arc and little arc. Okay, and then over here is the angle. That's your angle. So the measure of the big arc minus the measure of the little arc divided by 2 gives you the measure of the angle. Okay. And this one in particular is a big deal. It shows up all the time. So the 2 things that we've learned so far that show up a lot in problems this unit are the inscribed angles. So that's circle conjecture number 2. Circle conjecture number 2 shows up all the time. And then this one, circle conjecture number 8, shows up all the time. Big arc minus little arc divided by 2, all the time you're going to see it in lots and lots and lots and lots of problems, okay? And it shows up on the EOC too, like the EOC review problems I saw, there was lots of these. All right, so we're going to do big arc minus little arc divided by 2. So for this first one, we're going to say to solve for angle X, we're going to do 90 minus 20 divided by 2, and that's going to give us X. 90 minus 20 divided by 2. So 90 minus 20 is 70. 70 divided by 2 is 35. So X equals 35. Okay. So this one is an example of a secant line and a secant line. We have 2 secant lines that formed the angle there. In example 18, they have 2 tangent lines that were forming it there. 2 tangent lines. So here, the arc that is 240 starts from this point of tangency and then goes all the way around to this point of tangency. That's the arc that is 240. They did not give us the small arc, but if you guys can tell, the small arc is actually the rest of the circle. So if you wanted to find the small arc, what would you do? Yeah, so 360 minus 240 is what? 120. Okay, so 120 is the small arc. So now we're going to do big arc minus little arc divided by 2 equals the angle. And so 240 minus 120 is 120. 120 divided by 2 is 60. So we get 60. Okay. And then the last one, they have one secant line over here, and then over here they have a tangent line. So they did a mixture of the two. They told us that this arc over here is 120, this arc in here is 65, and we don't really care about the 120, but it is going to help us to find the big arc. So how could we find the big arc? What should we do? Okay, 360 minus 120. Is that going to give us the big arc, or should we do something else as well? Okay, so 360 minus 120 minus 65. And what does that give us? 175. Okay, so the big arc is 175. And then now we can do big arc minus little arc divided by 2 equals the angle. And so 175 minus 65 is 110, and then 110 divided by 2 is 55. Okay, so we got 55. Okay, perfect. So that is circle conjecture number 8. Circle conjecture number 9 is pretty common as well, but it's not as common as number 8. So number 8, definitely memorize. Number 9, memorize, but if you need to look at a cheat sheet, not a huge deal. Okay, so for this one, we have the measure of arc 1 plus the measure of arc 2 divided by 2 equals the measure of the angle. Okay, and so the angles that we have, and maybe go ahead and erase this. I'm going to just call it x this time. Instead of saying measure of the angle, I'll just call it x equals x. Okay, so here's the angle. This is angle x, and then because they're vertical angles, they're actually the same. So angle x could be this one or this one. It doesn't really matter. And then the arcs are up here. We'll call this arc 1. And down here, we'll call that arc 2. So you don't necessarily have one is big, one is small. They could be interchangeable as far as the sizes go, but you add them together and divide by 2. So the interesting thing about this is that the angle is not necessarily a central angle. The point where the X is made, the point where these cross, it's not necessarily in the center. So now we've had angles where you have a central angle. The angle is created using the center of the circle. We have inscribed angles. Those are angles where the vertex is on the edge of the circle. And now we've got these funky ones where the angle is just somewhere in the circle, the intersection of two chords. So we've kind of got all the different situations that could happen inside a circle now. So we just got to add them together, divide by 2, and that's how we get the angle. All right, so let's look at example 20. We're going to do 70 plus 116 divided by 2, and that's going to equal the angle. So 70 plus 116 divided by 2, and what do we get? We get, so be careful when you type this. If you look at it and if you do 70 plus 116 divided by 2 like this, you're going to get the wrong answer. So make sure you add 70 plus 116 and that both of those get divided by 2, and you should get 93. Or you can type it in like a fraction, 70 plus 116 divided by 2. You could type it in that way as well. But you do want to make sure that you do not type it in like this, because if you type it like this, only the second number is getting divided by 2, not the sum. We want the sum to be divided by 2. not just one of the numbers. So 93 is the answer you get. Okay, that's an angle, so we can say 93 degrees. All right, the next one. So here they put the x in a different spot. So the x is the arc, so we're going to say one arc plus the other arc divided by 2 equals the angle. And here we have a little bit more math to do since we're solving for the arc instead of solving for the angle. We actually knew the angle this time. So if you want to get rid of the fraction, how could you do that? Yeah, get rid of the 2 on the bottom. So times 2 times 2. So I've got 160 plus x equals 240. And then what should I do? Okay. So 240 minus 160 equals 80. Can anyone see what is funky about example 22? There's something weird about it. It's for the angle, but it's the wrong one. Yeah. So the 139 is not the angle we wanted. How could we find the correct angle? Okay. Okay. Because they're vertical angles. Okay. 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 So 360 minus 139 minus 139 gives you 82. And then we could take that 82 divided by 2. Okay, so these are both 41. Okay. Ava, is that what you were going to say, or did you have another method? Yeah. So, yeah, same thing, same idea, but you were using like a full circle as opposed to a straight line. So it's just two different ways of thinking of it, which is pretty common for these problems, that there's different ways you might interpret it, but still arrive at the same conclusion. So the other way you could think of it is, oh, this is on a straight line, and a straight line has 180 degrees. And that would help you to find that missing angle as well. Okay, so we're actually going to ignore the 139. The 139 does not work with our formula. So we're going to say now we have the arc plus the other arc divided by 2 equals the angle. And then we can solve it just like we did with example 21. So we can take the 2 and multiply it. Times 2 times 2. 40 plus x equals 82. And then subtract the 40. And so the missing arc is 42 degrees. Okay. And I think, is that it for the notes? That's the end? Okay. All right, so if we go back to our packets now, at this point you are done with 1 through 16, but now you can go ahead and use what we just learned to finish 17 through 22. So 17 through 22 is what we're working on right now. The last page is like a puzzle problem where it throws everything together, and this page is going to be extra credit. So if you go ahead and just write at the top extra credit. I'm gonna let you guys, I will wait until the end of the period to collect all the papers so that if you want to work on this at some point during the period, you can. So whenever I am doing these puzzles, I like to kind of organize my thoughts and work for the same type of angle at a time. So I look at this and I say, okay, 2 is an inscribed angle. Over here, 5 is an inscribed angle, so I might look at those kind of at the same time because inscribed angles feel pretty comfortable to me. 8 is a central angle, so I'm going to start with angle 8, angle 2, and angle 5 because those are my comfort zone. I had the most practice with those, and those are the ones that I feel the best at. And then from there, then I can start looking at the other ones that we studied. So the ones that we just did are ones like 4 and 6. That's where if you can find the 2 arcs, you can add the arcs together and divide by 2, and that's going to give you 4 and 6. It's going to give you both answers. The 3 right here, if you can find the arcs, you're going to be able to add the arcs together on either side. If you can picture this as a big X right here, you can find the arcs on either side, add them together, divide by 2. 1 over here is that angle that's outside the circle, so if you can find the big arc minus the little arc divided by 2, then you can get angle 1. So I like to go, instead of thinking of it as a huge puzzle that's kind of hard to solve, I look at the individual pieces that are comfortable for me, and then the more that I label in the picture, the easier it is to find the ones that are not as comfortable. Does that make sense? That's a good approach, because there's a few different times I will put these in the packets, and I just want you guys to have kind of a strategy for approaching them so they don't feel as frustrating. Okay, so it's extra credit this time. And so right now we are working on 17 through 22. I'm going to give you guys some time, and then we're going to move on to the segments assignment. Sound good? Okay, so go ahead and work on that. All right. Are there any problems that you guys have seen on the segments assignment that have given you pause, that you think might be too difficult, anything that you would like to look at together? Based on last night's notes, you should have been able to do 1 through 12. 1 through 12. So we just want to make sure that none of those look too intimidating. Is there anything that just seems weird? Everything? Mm-hmm. Do you guys want to go over any of the problems together? No, if you finish the first assignment, you could get started on this one because you already took the notes. So is there any problem that you guys would like to do together just because you're not really sure how you would do it? What do you guys think? This is based on last night's notes. Are you looking at it like... These ones are pretty simple. We haven't really done the difficult examples yet. I think these ones are the ones that are a little bit more straightforward. But if the pictures mess with your brain, then we can certainly go over one of them. You just have to tell me which one you don't like. So is there a problem you guys want me to do? We don't like 4? We can do 3. Okay, so if we look at 3, number 3 is using circle conjecture number 10, which just says that if you have tangent lines outside of a circle that meet at an exterior point, then those 2 lines, they just have to be the same length. That's all that it's saying. And so in 3, you just have to mark down what each of the little lengths are and then be able to add them up to find the whole perimeter. And it's almost like a domino effect. If you can start to mark down a few numbers, then you're able to get the rest of them. So here they give you like what the entire length is, what the entire length is, what the entire length is. But the key to being able to do number 3 is that they tell you that this length right here is 8. And if this length is 8, that means that this length is 8, because they have to be the same. So just like circle conjecture 10, if you have 2 tangent lines that meet at an external point, then the two lengths have to be the same. So if, I'm going to show you guys, if this length right here is 8, then this length right here has to be 8 also. That's how that works. So I'm just going to label 8, and then this one over here is 8. So if the whole thing was 14.5, and that part of it is 8, then what's this part of it? 6.5, okay. So that means that this is 6.5. So if this part is 6.5, then this part also has to be 6.5, because that's what circle conjecture number 10 says. Okay. So that portion is 6.5, the whole thing is 14.1. So if that whole thing is 14.1 and this is 6.5, then what does this piece have to be? 7.6. Okay? So if this part is 7.6, then that means that this part is also 7.6. Okay? So if that is 7.6 and the whole thing is 11, then what does this piece have to be? 3.4. Okay, so if that's 3.4, then this has to be 3.4 also. Okay, so now we just have to figure out what the perimeter is. So go ahead and add everything up. However you want to add it up is fine. And anyone want to say what they're getting for the perimeter? 51. Anyone else want to confirm 51 is what they got? 51? Agree? Everybody else agree? 51? Okay. All right. Is there... So we said 3 we wanted to do. Was 4 the other one we wanted to do? We can look at... So 5 is actually just like number 3. It's just an equation version. So we have 2 tangent lines. They meet at an external point. That means that the 2 tangent lines have to be the exact same length. So that if they're the exact same length, what should we do? Set them equal to each other, yeah. X plus 17 equals 3x minus 1. They got to be equal. Okay. 4 and 6 are the same. So 4 and 6 are kind of referring to circle conjecture 11, which says that if 2 well, actually it might be... No, I think it is that one. If 2 chords in a circle are congruent, then their arcs are congruent, except we kind of have the backwards version going, where we have the arcs are congruent, which means that the chords are going to have to be congruent. It just is kind of saying that they come in pairs. So what we have here is we have that these chords, or that we have the arc CD and the arc AB, that those were marked as being congruent. And since those are congruent, that means that these two have to be congruent as well. So in this picture, same thing over here in this picture, if we have this arc is congruent to this arc, then the chord has to be congruent to the other chord. So if you know the chords are congruent, how are you going to solve for x? If you know the chords are congruent, that means they're the same. How are you going to solve for x? You're going to set them equal to each other. Yep. So for 4, 5, and 6, we just have some pretty simple equations to solve. And I think the reason that I like these problems is if somebody put this on a math test and I had to guess how to do the problem, that's probably what I would have guessed anyway. It's like, what else would you do with that? I don't know. So for the most part, I think students tend to get these right, even if they don't remember it. Because it doesn't seem like there's a whole lot else you could do. Okay. How do we feel about 7 and 8 and 9? Actually good?
Yeah.
We got them? So 8 and 9 are getting at circle conjecture 13. So they're kind of showing you that distance, how far away the chords are from the center. And if they're the same distance away from the center, that means that the two chords have to be congruent. They have to be equal in length if they're the same distance from the center. So in 9, you can really see it. They're both a distance of 8 from the center, which means the two chords have to be the same. In number 8, they say AB and BC are congruent. So they're saying that the chords themselves are congruent. And then from that, you're solving for DF and FE. So if the chords themselves are congruent, that means that their distances from the center would have to be equal. So they're kind of like the opposites of each other, the two problems are. But same type of idea. Can anyone tell me what x is in problem 7? Yeah, it's 16. How do you know it's 16? Yeah, it's just another radius. So that's something that actually is really helpful in these problems. X equals 16 because x is just a line from the center of the circle to the edge of the circle, which means that if you can find the radius somewhere else, this is just the length of a radius. You don't have to solve anything with triangles to be able to solve that. You just have to recognize, oh, it's a radius of the circle, and I already know what that length is. Yeah. Yeah. So number 10 still uses the idea of a radius, but it's actually going to make you do some more math. So what I'm going to do here, you can kind of see they gave you a radius already. They said that that was 13.6. So what I'm going to do is I'm going to form a triangle right here. And if you can see, what I'm doing is I'm completing a right triangle. Does everyone see that? And I drew in the hypotenuse, and the hypotenuse of that right triangle happens to be a radius. Everyone see that? So I drew in the hypotenuse, but it's a radius of the circle. So since it's a radius, I know that the length is what? I know it's 13.6 because it's the radius of the circle. Okay, now we need to find this length x right here. So we're not there yet. I'm going to go ahead and call this y because it's an unknown, but it's different than the unknown that we're actually trying to solve for. So what I have right here is I have a right triangle. I have 13.6 for one side, 12.6 for another side, and then the third side I have a y. So if that is what I have, how would I set up the Pythagorean theorem? What would I do? Perfect. So the strategy that I used here of drawing in a radius to make a triangle, it's a very common strategy. So it's not like, oh, Miss Rice, how did you know to do that? I saw somebody do it once, and then I went, oh, that works like all the time. You can like do that often. You can like typically make a right triangle and do this. So that's what made it so I knew how to look for that. Okay, so I'm going to do, in my calculator, I'm going to do 13.6 squared, and I'm going to subtract off 12.6 squared. And I know that when I do that, that's y squared equals that number. So I got y squared equals 26.2. Is that what you guys are getting? Yeah? Okay, and then what should I do? square root it. Okay. So y, I'll just do 1 decimal point because that's what they're doing. So y is approximately 5.1. Okay. Now what I want you to notice is that y and x added together is the radius. Does everyone see that? Y and x added together is the radius. So if I want to know what x is, what should I do? Yeah, 13.6 minus the answer that I just got. And then that means that x is what? 8.5. So similar in number 12, this is a similar problem to number 12. Can you draw a radius somewhere and make a right triangle? Yeah, where can you draw the radius? Yeah, by the 17.3. So from the center to the 17.3, you can draw this radius. And so the radius is the 20.9. And then here's your right angle. And then there's the x, that's what we're trying to find. We can just call that y. And then it's exactly like the last problem we did. So it's a really common strategy. Yeah. Yeah, so the reason I drew it over here is because sometimes students are uncomfortable taking this measurement and moving it over. It's a lot more comfortable to say the radius is the same. For sure, a radius is a radius. Do I know for sure that this split that in half? I feel less comfortable making that assumption. It's true, but I feel less comfortable with it. I feel really comfortable saying a radius is a radius. Does that make sense? So yeah, it would have worked if you'd done it the other way too. Yeah, good question. Okay. So I'm going to give you guys about 5 minutes to work on some of those, and then we are going to finish up our notes. All right? Okay. Girl, this whole time. Yes. Okay, so you go to Canvas. I'm going to show you. You go to Canvas, you click Modules. Yeah, it's how this unit goes. It feels like a lot. Okay. Yes. Yes, it is. Now you know why. Yeah. All right. So for any given point in a circle, are you guys ready? The product of the two segments from the point to the circle is constant along any line through the point and the circle. So we have 3 situations that we can deal with. And we're going to go ahead and write them. And what I've noticed is that these are pretty common. So if you go back through your notes, let's look at these. As far as like what you're going to often see throughout the unit, like the problems that are more common, this is pretty common. So the tangent lines outside, knowing that they're equal, that's definitely something that is going to show up. The chord and the arc length being the same is kind of like, there's a few problems here and there, but not a ton of them. And then the ones that you're really going to see a lot of, more so, from what I've noticed, are these ones. So as far as like, not all of the problems are represented equally. That's kind of what I'm telling you, is that some things are stressed more than others. And this seems to be one of the things that's stressed a little bit more. Okay, so for this, when they talk about the length of C, they're talking about like just this part. This is the length of C, this is the length D. And then that's the length A, that's the length B. So the formula for this scenario is that A multiplied by B equals C multiplied by D. So basically, the two segments that form one line, if you multiply them together, they're going to equal the product of the segments that make the other line. Now, for the other two situations, I'm going to write down the formulas based on this picture, but I don't really want you to use these formulas. I want you to use the concept of how it works. So I'm going to tell you the concept of how it works first, okay? So the concept of how it works first is you take the entire line, and you multiply it by the outside, the part that's outside the circle. So it's entire line multiplied by the outside equals the entire line multiplied by the outside. That's what it is, okay? So now I'm going to show you how that works specifically in situation 2 versus situation 3, okay? It's the entire line multiplied by the outside, entire line multiplied by the outside. So for situation 2, the entire line is x plus w. Does that make sense? That's the entire thing, x plus w. X plus w. The outside is w. So it's x plus w multiplied by w. Then for the other one, the entire line is z plus y. That's the entire line, z plus y, multiplied by the part that's on the outside, which is y. So the entire line multiplied by the outside equals the entire line multiplied by the outside. Does that make sense? So instead of labeling things, just think about how the pattern works instead. It's easier than trying to memorize. Okay, now for this one, what's the entire line? T, okay. T, what's the outside? T, so T times T, okay? Then for this bottom part, what's the entire line? Z plus Y, there you go. The alphabet's hard sometimes, you know? And then what's the outside? Y. So T times T equals Z plus Y multiplied by Y. So the entire line multiplied by the outside, the entire line multiplied by the outside. So they're different, but they're the same. Does that make sense? They just follow that pattern. Entire line multiplied by the outside, entire line multiplied by the outside. Okay, are we ready to try it? Okay, so what's the length of the entire line? 6 plus 8, which is 14. Okay, and then what's the length of this entire line? 7 plus y. Okay, so we're going to say 14 times, what's the outside? 6, okay, equals 7 plus y times the outside, 7. Okay, and then we just go through and solve the equation like normal. So 14 times 6, 84, and then distribute the 7, we get 49 plus 7y. And then what happens if you do 84 and you subtract the 49 over? Okay. And then what do you get for y? Y equals 5. Okay. Okay, so let's do the formula for this one. What's the length of the whole line? Z, okay, trick question. What's the length of this whole line? 24. Okay, so we have the whole line multiplied by the outside. What's the outside? Z, okay. You're good. And then over here, the whole line is 24. What's the outside? 8, okay. So we have Z squared equals, and then what's 24 times 8? 192, okay? And so to solve this, we're just going to go ahead and square root. We know that whenever we square root, we always get two answers, but because we're talking about a length here, we can't have two answers. We can't have the positive version and the negative version. Only the positive version makes sense. So what do we end up getting? $13.9? What was it? A couple, maybe three? 856. You're fine. 13.856. Okay. How are your brains feeling? Good? Okay. Doing okay. Okay. All right. So the whole thing, we got a 12, we got a 14. What's the whole thing? It's a 20. Sorry, I said 12. I meant 20. It was a typo. It was a typo when I read it out loud. 20 and 14 is 34. Okay. X and 16 is... Okay. All right, so we're going to do the whole thing multiplied by the outside, which is... Okay. And then we've got the whole thing multiplied by the outside. 16, okay. So 34 times 14. 16 times 16 is 256, is that right? Oh, Miss Rice, well, bam. No, nobody? Okay, it's fine. 220? So what does x equal? Okay. Okay, and then how do we do the last one? We multiply the two things that appear to be on the same line. So which ones look like they're on the same line? Okay, so 3 times 7 equals... Equals? Okay. And then what should we do? Divided by 6.5, what do we get? Oh, something nasty. 3.231, is that what you guys got? Okay. Ta-da! Alrighty, so if we look back at the packet we are working on today, you have the next section, which just focuses on those, and then the section after that mixes them up. So does circle conjecture 10 through 13 and the power of the point theorem, kind of mixes them together. As you guys are looking, are there any problems 13 through 21? Are there any problems 13 through 21 that feel intimidating? We can do 13. Um, 15 could be good to do. You guys want to do 15? Or 16? You guys want to do 15 or 16? 16. Okay, let's do 16. All right, so the whole thing for that one is x plus 3. What's the whole thing for this one? Okay, so x minus 1 plus 10 would be... Wait, what would it be? 9 plus x? Okay. All right, so we have the whole thing times the outside equals, on the other one, the whole thing times the outside. Do you guys see why I said let's do 16? Okay. So how do we deal with this when it's got two sets of parentheses on each side? We got to FOIL. We have to FOIL, and we have to FOIL twice. We have to FOIL on the left side of the equation, and we have to FOIL on the right side of the equation. So when you FOIL on the left side of the equation, what do you get? Yeah. Okay. And then when you FOIL on the right side of the equation, what do you get? X squared, 8x minus 9. Okay. And then the thing that works out kind of nice is that since you have an x squared on each side, they cancel out. X squared and x squared, because you have exactly the same thing. Kind of like the problems where there was like a pi and a pi on each side, you could just get rid of them. Okay, so we have 6x plus 9 equals 8x minus 9. What should we do? Do what? Okay. Then we could move the 9 over. So what does x equal? Okay. So I'm not going to have you guys do the video notes tonight. I'm just going to have you guys finish this packet. Does that seem reasonable?